Now the NPC will try to get to my position if I'm hidden. Let's run away in front of them. Let's hide. Let's quickly hide. Yeah, I'm dead. So after a while, the NPC will forget about the detection entry for the player and will go back to its post. Okay, so he's going to shoot me, then wait, then shoot again, then wait. Let's try to escape. In this GDC talk that I talked about a couple of videos ago, I'm going to go over the part by Bobby Angelov. Of course, I encourage you to watch the talk in full. It is chock full of informations and really great advice on creating behavior trees and making AI behaviors in general. I apologize for the low quality of the screenshots because the video on YouTube is 720p max. So I really love the ideas put forward by Bobby Angelov. I love that he gives a definition of what a behavior tree is. So at its core, a behavior tree is a mathematical model of plan execution. What this means is we imply that a plan already exists. He says that behavior trees are excellent for describing a complex sequence of actions to perform. So they're excellent for describing how a plan should be executed, but they are poor at actually creating that plan and making decisions. And I completely agree with him. So he talks about the advantages of a finite-state machine over behavior trees in some aspects. So he says that state machines are excellent for describing states and transitions. They are simple, easy to visualize, but they are bad for defining sequences of actions, which behavior trees are good at. So behavior trees are excellent for describing sequences of actions and for parallel execution of actions, but they're bad at defining transitions and reactions. So in an ideal world, we'd combine the benefits of a state machine with the benefits of a behavior tree, and we'd use a hybrid solution. One thing he mentioned as well, state machines are cyclic graphs and they are very good at transitioning back and forth between multiple nodes in the graph. However, a behavior tree is an acyclic graph, so it's very good for defining static priority. For example, if you use a selector, the selector considers that its children are sorted from high priority to low priority. So the behavior tree's weakness is that lack of a cyclic behavior that we can compensate with a state machine. As for planning and making decisions, we either use a state machine or we use another kind of planners. We could also use goal-oriented action planning for that aspect. So forcing a behavior tree to have a structure for decision making is very hard. We are abusing the behavior tree and scaring new people away. And I experienced this in my game dev journey because you can indeed make a behavior tree do anything you want, but at the cost of adding a lot of complexity. And he says that we are struggling to implement simple concepts and drowning in our own complexity. Yes, because the concept of a finite state machine is very simple. Trying to recreate that with a behavior tree can get very complex. So why not just use a finite state machine? So here are his conclusions. So behavior trees are excellent at describing individual behaviors. We can use them to define the execution of decisions. We can keep them as small and as simple as possible. And we can combine them with other techniques to get the most out of them. And what behavior trees are bad at is they're pretty bad with interruptions and transitions. And we should not build cyclic behaviors with a behavior tree, which is an acyclic data structure. And we should stop building large monolithic trees with multiple responsibilities. In our behavior tree system, we could create a finite state machine task that could totally work. However, we've already implemented something that works like a finite state machine and could even work better than a state machine in some cases. And that is a utility selector. Indeed, we could use a utility selector like a finite state machine instead of defining transitions like we would do in a regular finite state machine. Each state would define their utility and the selector will transition to the state with the highest utility. So we get the element of simplicity of FSMs with the cyclic behavior. and we build on top of what we already have. Normally, we would not change anything. We already have all the tools that we need to implement this. However, one of the downsides that we have is that we'll have to create new action classes just to define the utility of each of these states. And that could be a lot of work. We don't want to create a dozen classes just to implement the behavior of one NPC or just part of that behavior. So we want a better solution, and that's what we're going to do right now. By the way, I'm using FreePlane. It's a great mind mapping tool. You can use it for brainstorming game design ideas. And in our case, in this course, we're going to use it to design behavior trees. You can customize the keyboard shortcuts to make it very fast to use. My only requirement for a tool like this is that it has to be faster than pen and paper. And in this case, it totally is. So I highly recommend using it for all your brainstorming needs and also for thinking about and designing behavior trees. Let's go to the behavior tree that we created a couple of episodes ago. So let's go to AI Mastery, Behavior Trees, Scripts, Test Interruption. I just want to take a look at this code. So in here, if we want to define a custom utility for one of these actions, we have the option of setting the default utility. So for example, I can go to any action and I can set default utility to 5, for example. So we have the option to do that. However, if we have something more complex, if we want to execute some code, for example, have some if statements, if I have a visible target, then I'll set the utility to 10, for example. If we want to do stuff like this, we'll have to derive from the action class and then define the utility there. But that is slow. So imagine having to create a new class every time you want to use a single action. We want something faster. So we're going to create a custom action class that uses actions and functions to expose all the methods of an action, and we'll mainly use it to define a custom utility. So let's go to our scripts folder, task system. Then we're going to create our class in the base folder. Let's call it custom action. Let's put it in the game.tasksystem namespace, and it's going to inherit from the action class. We want to prevent ourselves from deriving from this class, so we're going to add the sealed keyword. Let's define some Unity actions and functions. For the Unity actions, we'll have awake, entry, and exit. As for the system functions, we'll have update and utility. Since the task class already has an update method, which is a static method, we're going to use the new keyword here, but it shouldn't matter because we're not going to be using task update in here. And remember to use the Unity engine.events. Let's override the methods of the action. First, we override the onAwake method. Then we call invoke on the awake action. And we use the question mark here. This is equivalent to saying if awake is not null. We do the same for the onEntry and onExit methods. Then we override the onUpdate method. If our update func is not null, we're going to invoke it and return the result. Otherwise, we return task status success. We do the same for the getUtility method. So we override it here. If utility is not null, we're going to invoke it and return the result. Otherwise, we return the default utility. So the utility func has the full responsibility of returning the utility. So if you do use a custom action, you'd have to decide what to do with the default utility if you want to return the default utility plus another value, or if you want to completely ignore the default utility and return your own value. So we have the freedom to do whatever we want, but we should be aware that we'll have the full responsibility of what this function returns. Now let's go back to our test interruption behavior tree. Let's test the custom action here. So in this sequence, we're going to add a new custom action. In C#, we can instantiate the class and define its properties between brackets. We'll assign lambda expressions to each action and func. When the action awakes, we're going to print awake on the console. Same on entry and exit. Then in the update, we're going to return success. And for the get utility, we're going to return 250. So this is a really compact syntax. We didn't have to create a new class and instantiate it here. Let's say we want to access the NPC or another object on the owner. We're going to need to access the owner. So going back to the task class, here we define the owner as a protected property. Let's make it public with a protected set. Then going back to our test interruption behavior tree. So we can use the owner here. or we can get it in here. So let's get the NPC. Let's get it from the sequence. Sequence owner get component in parent NPC. Then we can use the NPC right here. If NPC carrying gun, let's return a value of 5, for example. So this is just an example. This doesn't make any sense, but I'm just showing you how to access components on the owner just for the sake of testing. When we enter, we're going to print the name of the NPC, npc.name. We have a null reference exception in test interruption. So the problem is at this stage, the owner is not defined yet. So we'll have to do it inside of the Lambda expressions. So what this tells me is, like we did for the NPC action and NPC condition, we'll have to create a custom NPC action. If we run the game, we get an awake message here. We also get an entry and exit, which tells me that we probably have to revisit how the conditions work inside of composites, because the selector is still executing the sequence, even though its conditions are false. Let's test the rest of the action. Let's get in front of the character. So the action has entered and exited. So our code is working. So I'm going to comment out this action here. So we're going to create an NPC custom action that will do pretty much the same thing, except it will have a reference to an NPC and the sensor. I'm going to go to custom action. I'm going to select all of this code, then copy it inside a new class. We're going to call it NPC custom action. Then we're going to go into our NPC action. We're just going to copy this and back to the NPC custom action. We're going to paste it here. So in the onAwake method, we're going to get the reference to the NPC and the sensor. Then we're going to invoke the awake action. Let's remove this from here. Since this is a sealed class and we're going to access these from outside, we're going to have them as public variables. So I'm going to rename them to have capital letters, and we're going to have them as public fields. Okay, and the rest of the code should be the same. Now, if we go back to our behavior tree, let's uncomment the code, and we're going to use an NPC custom action this time. To be able to access the NPC variable inside of the custom action, we can't access the properties of the NPC custom action if we use an inline declaration like this. We'll have to create a variable, let's call it action, then assign each action after we instantiate the variable. This way, the action will be fully formed and we'll be able to access the NPC field like this. So let's remove the rest of the code and let's add the action to the sequence. Now let's test the action. As you can see, it has printed entry NPC once when we started the scene, then once again when the combat sequence has started. So using a syntax like this is fine. However, I really like the inline declaration that we had before. So one thing we can do is pass this action as a parameter here in the Lambda expressions. So let's go back to NPC custom action. The problem when we use the inline declaration is that the action object is not fully prepared yet, so we cannot access it. But if we pass the same action as a parameter in the Unity actions and functs, then we can have access to the action, and by consequence, we can have access to the NPC and the sensor, even in the inline declaration. So let's make the changes. Let's add an NPC custom action on each Unity action and on each func as well. Now in the overrides, we'll have to pass this object here. So we're going to use the this keyword everywhere in the onEntry, onExit, in the update, and in the utility. Now back to our behavior tree. I'm going to hit Ctrl Z to go back to our inline declaration. Now we have to use a parameter here. Let's call it action. This is a small trade-off to be able to use this inline declaration, which is really practical. So in here, instead of NPC, we're going to say action.npc. And here we don't need to get the NPC. We can just say action.npc. And this syntax is much more compact than before. We're going to use the same structure that we did before. Let's rename this mind map to Sentry AI. So we're going to have a selector at the root, and we're going to have a combat branch and an idle branch. In the combat branch, let's add the has hostiles condition like we did previously. And in the idle branch, let's just use the idle action. So while we are in the idle branch, the selector will keep evaluating the conditions of the combat branch. The idle branch will be interrupted, and the selector will switch to the combat branch. However, we could add some nuance here. What if we wanted the combat branch to only interrupt when we have visible hostiles? This will work, however, we will have problems here. Let's say our guard has one hostile. As soon as this hostile gets out of sight, the combat branch itself will be interrupted, and the selector will go back to the idle task. What if we wanted the conditions of the combat branch to only interrupt and not be evaluated every time? So we're going to have to separate between normal conditions, which are the conditions that are always evaluated, and the interruption conditions, which are the conditions that will only be used to interrupt lower priority branches. When we are inside the higher priority branch, these conditions will no longer be evaluated. So this nuance will be very useful in a lot of situations. So the has visible hostiles will be an interrupt condition rather than a regular condition. So let's go ahead and implement a different list of conditions. Let's call them interrupt conditions. Let's go in our script, then the task system folder, then the base, and let's go into the composite task. Let's create a new list here called interrupt conditions. Let's go into the conditions methods region. We're going to copy these methods and let's use them for interrupt conditions. So we're going to rename the first one to set interrupt conditions, and we're going to set our interrupt conditions here. Then we're going to rename add condition to add interrupt condition. Then we're going to rename evaluate conditions to evaluate interrupt conditions. And we're going to use interrupt conditions here instead of conditions. Our evaluate conditions methods evaluate the conditions such as all conditions should be true. It's like using an if statement where we have condition 1 and condition 2 and condition 3. What if we wanted to change this and to an or? So instead of using list here, why don't we use a composite condition? And in there, we'll have an opportunity to define the evaluation mode. Let's go ahead and create a new class called composite condition. Let's put it in the game.taskSystem namespace. It's going to inherit from condition. We're going to override the onUpdate method, but we're going to seal it. You know what? Let's go ahead and seal the entire class. We don't want to derive from it at any point. Let's define a list of conditions. And here I've copied these methods from the composite class. Let's define a public enum called condition evaluation with an and an or value. And let's define a public property in the composite condition called evaluation, which will be set to and by default. In the evaluate conditions method, our evaluate condition uses the and mode by default. So here we're going to say if status is failure and the evaluation mode is set to condition evaluation.end, we're going to return false. Otherwise, if we are in the or mode and at least one task succeeds, then we're going to return true. Then when we're out of the loop, if the evaluation mode is and, we're going to return true. Otherwise, we're going to return false. Then in the onUpdate method, if evaluate conditions is true, we're going to return success. Otherwise, we're going to return failure. Now let's go back to our composite class. Instead of using these lists, we're going to use a composite condition. We're going to use a composite condition for conditions and for the interrupt conditions. Let's rename them to just condition and interrupt condition. That would be more appropriate. Now let's go to our condition methods. In set conditions, we're going to call condition set conditions. Same for add condition. Since we have a condition parameter, I'm going to use this condition, then add condition with the condition parameter. In evaluate conditions, we're going to return condition.evaluate conditions. And we're going to do the same thing for the interrupt conditions. You know what? We could simplify the syntax. Let's go back to our composite condition. We could simply rename evaluate condition to evaluate. Let's rename condition evaluation to condition evaluation mode. And here for the evaluation, let's rename it to evaluation mode. I feel that these names are more expressive. Now let's go back to our composite condition and let's override the rest of the methods. We're going to override the onAwake method, in which we're going to loop through our conditions and call task.awaken on each condition. We're also going to override the setOwner method. We're going to loop through the conditions and set the owner for each condition. Back to our composite task. In the setOwner method, we're going to call setOwner on both the condition and the interrupt condition. Same for the onAwake method. We're going to call task.awaken on the condition and on the interrupt condition. Now let's go to our selector. Let's go to tasks, composite, then selector. In the shouldInterrupt lower priority method, we're going to change the evaluate conditions method to evaluate interrupt conditions. Let's do the same thing in the sequence class. In the shouldInterrupt lower priority, we're going to use evaluate interrupt conditions. Let's fix a problem that we uncovered earlier in the video. If the condition on a composite evaluate to false, we shouldn't even start the child tasks. So we're going to go over each of our composites and fix the problem, starting with the sequence. So in the onEntry method, we directly start the first child. So before doing that, we're going to check if condition evaluates to false. If so, we're going to return. We're not going to do anything in the selector since it's inheriting from sequence and it's not overriding the onEntry method. However, we're going to do it in the parallel task. Same here in the onEntry method, we're going to evaluate the conditions. If they are false, we're going to simply return. Let's check the parallel selector. So it inherits from parallel and it's not overriding the onEntry method, so we're not going to do anything here. Let's go to the utility selector. So in the onEntry method, it's not doing anything, so we're fine. Okay, back to our mind map. So as soon as we have visible hostiles, we're going to switch to the combat branch. So we'll have to define a has visible hostiles condition. Our combat branch can actually be a parallel, and in here we can have a repeater that will constantly pick the best target, and our repeater will end on a failure. So we're going to implement a pick best target action, and in here we can have a utility selector. This utility selector will handle gun management, so it will choose whether to shoot, reload, or wait in an idle state. Then we're going to follow the target, set aim to true, then look at the target. As for the idle branch, it could be a simple sequence where we get the post position. So the post at which the sentry is supposed to be standing, we could have it as a transform. So we get its position, we go to it, then we look in the direction of the transform, then we go to an idle action. So in here, perhaps we need to cancel aiming. So we're going to set aim to false, and we're going to put it at the top of the sequence. Let's implement this little by little. We're going to implement this idle sequence first. Then we're going to move on to the combat branch. Back to the editor. We already have an NPC here from the previous videos. Let's use this as a Sentry. So let's rename it to Sentry NPC. Let's go to Content, Prefabs, NPCs, and we're going to save it as a prefab variant. Let's go into the prefab. So in here, let's put this AI object at the top. So we're going to create two scripts. The first script is going to be our behavior tree, and the second script will be a Sentry script that we're going to use as a blackboard. We're going to define the post transform here, and our actions will be able to access that component using the owner object. So let's go to our scripts, or I should say to behavior trees, scripts. Then let's create a Sentry script here. You know what? Let's create a folder. Let's call it Sentry. We're going to create our behavior tree here. Then let's create a subfolder called Blackboards. And let's create a Sentry script here. Both our behavior tree and our Blackboard have the same name, but they're going to be in different namespaces. So this is our Sentry external behavior tree. So we're going to put it in game.external behavior tree. Let's inherit from external behavior tree and override the create behavior tree method. Let's add a create asset menu attribute. And in the create behavior tree method, let's create a selector and return it. Let's add a combat branch and an idle branch to the selector. In create combat branch, we're going to return a new custom action that will return failure in its update method because we want to focus on the idle branch for now. So we're going to create a sequence here and we're going to return it. Then we're going to add a set aim set to false. Then we're going to declare a shared vector tree post position. we're going to define the update func using a lambda expression where we're going to get the Sentry blackboard. Make sure to use game.sentry as to not confuse it with our behavior tree. Then we're going to set the value of post position to sentry.postPosition, and we're going to define this shortly when we create the Sentry class. Perhaps let's also get the direction of the post. Let's declare a post direction shared vector tree, and we'll also have to define a post direction on the Sentry class. Then we return success. Here I'm going to give the NPC custom action a name, just so we understand what it does on the behavior tree viewer. Then let's add a goTo action with the destination set to post position. Then let's add an idle action. And here, between the goTo and the idle, we're going to make our NPC look in the direction of the post. Let's create a new custom action named lookAtPostDirection. In its update method, we're going to set the target position to post position.value plus post direction.value multiplied by 30. We're going to make the NPC look at the target position. Then if NPC is looking at target position, we're going to return success. Otherwise, we're going to return the running status. So as you can see here, if you don't want to create a dedicated action for this, you can do it in a custom action, which gives you a lot of freedom to write code without having to create many classes. So now let's go ahead and define the Sentry blackboard. We're going to need a post position and post direction properties. So let's go into blackboards, then Sentry. We're going to define a transform post. So just for the sake of visibility, I'm drawing gizmos. So I'm drawing a wire sphere at the position of the post, and I'm drawing a line between the post position +1 on the up vector. Then I'm drawing a line to display the direction of the post. So let's go ahead and define post position and post direction. So post position, we return post.position, and post direction, we return post.forward. Now back to our prefab in the AI object. We're going to need a Sentry here, and let's create the behavior tree. So let's go to our behavior trees here and right click, create game behavior trees Sentry, and let's assign it over here. Okay, let's get out of the prefab view. In our Sentry object, we'll need to define a post. So let's create a child object here. Let's name it guard post, and let's take it out of the prefab. So let's go to our AI object and set the guard post to this. Then let's move the guard post somewhere. Let's say we want it to be over here, and we want the NPC to look in this direction. So our NPC will stand near the wall and we look in that direction. So our selector has skipped the first task, which has failed. Then it has set aim to false. Then has gotten the post info. And now it's executing the goTo action. So it's going to go to the post. Then look at the post direction. Then go to the idle action. So our idle behavior is working fine. Now let's start implementing the combat branch. Let's go back to our Sentry behavior tree. Let's create a parallel task that we're going to return. We're going to add a hasVisibleHostiles to the list of interrupt conditions. Then let's add an idle action. So our goal here is just to test if interrupt conditions are working. We're going to define a hasVisibleHostiles condition. Let's go to scripts, NPC tasks, conditions, sensors. We already have a hasHostiles condition. Let's just duplicate it. And in the onUpdate method, we're going to check if visible hostile count is superior to 0, and we're going to return success. Otherwise, we return failure. Back to our Sentry behavior tree. So perhaps here, let's add a set aim action. Yeah, this is not going to work because the selector is stuck in the combat branch. So let's add a condition here. The condition will be hasHostiles. Okay, now it's working. So I'm going to hide. So the Sentry is at his position. I'm going to get in front of him. So as soon as I do that, he's going to switch to the combat branch. Yeah, it's not working because we need to set interrupt lower priority to true on our parallel. And now it should work. So let's get in front of the NPC. Now he has switched to the combat branch, as you can see. Let's add following the target and looking at the target. Let's add a repeater with a lookAtNPC here. We're going to need a target variable. Let's define it at the top of the Sentry behavior tree. It's going to be a variable of type shared NPC. And let's remember to instantiate it. It's very important that it's not null. So now we are looking at an NPC, but the value inside of target is going to be null at the moment. Let's create an action that will select the best target. So I created this class in scripts, NPC tasks, actions, combat. It's going to select the closest visible hostile NPC and maintain it even if it's out of sight. When a better target presents itself, then it will select that instead. So we're going to need a target of type shared NPC. Then let's define a method that will evaluate the score of the target. So if we have multiple targets, this function will give each target a score. If target is null, we're going to return 0. Then we're going to compute the distance between the NPC and the target using npc.getDistance. To be honest, I don't remember if I've covered this, but this is a simple shortcut. Let's peek into the definition. So in the NPC script, this is a simple shortcut that will get us the distance between the position of the NPC and the position of the other NPC. Then we compute the normalized distance score using mathf.inverseLERP between 5 and 40 using the distance. So if the distance is at 5 or something lower than 5, this method will return 0. And if the distance is at 40 or something greater than 40, then this method will return 1. And if it's somewhere between 5 and 40, it will return the appropriate value between 0 and 1. So we compute the distance score using mathf.lerp between 1 and 5 using that normalized score that we computed earlier. Then we compute a visibility score. If the target is visible, we're going to return 5. Otherwise, we're going to return 2. Then to compute the overall score of the target, we're going to return the distance score plus the visibility score. So I made a mistake here. So in the lerp, the first value should be 5 and the second value should be 1 because the closest targets should get the higher score. So let's define a pick best target method. Here we're going to declare a new target variable and we're going to look for the best target in sensor.detectionList.list. So we're going to loop through it in a for each loop. If entry is visible and hostile and alive and the NPC is different from new target, we're going to evaluate the target score of the new target against the entry.npc. If the score of the entry.npc is higher, we're going to set new target to entry.npc. Then when we get out of the loop, we're going to check if new target is not null. So if we found a new target and evaluate target score of that new target is higher than the score of our current target in target.value, then we're going to set target.value to that new target. Then in the onUpdate method, we're going to call pick best target. If target.value is not null, if the detection list no longer contains the target, it means that either the target is dead or that entry has expired, in which case we have to cancel the target. Then we'll check if target value is null. In this case, we'll return failure. Otherwise, we'll return success. Back to our Sentry behavior tree, we're going to use the new action here. So let's add it over here, parallel. Add task. We're going to do it in a repeater. So we're going to constantly be checking for new targets. And it's going to use our shared variable here, target. So this syntax could be confusing, but remember that target is the variable inside of select target. And this target over here on the right is our variable here. So these actions will share the target variable and will read and write its value. We need this repeater to end on failure. So we'll add it between brackets over here. Now let's implement the follow target action. In scripts, NPC tasks, actions, locomotion, let's add a follow NPC action. Here we'll have a target shared NPC and two parameters, max distance and mean distance. The NPC will try to maintain this distance from the target. In the onUpdate method, if target is null, we're going to fail. Otherwise, we're going to call a maintain distance method. Then we're going to return the running status. Now let's define the maintain distance method. So we're going to compute the distance between the NPC and the target. And we want the NPC to run when he's far from the target. So we're going to compute a t parameter using mathf.inverseLERP, which is going to go from max distance.value to max distance.value multiplied by 1.5. And we'll give it the distance value. Then we're going to set the max speed of our NPC to mathf.lerp between walk speed and run speed using the t parameter. So in other words, if the target is at a distance between max distance and 150% of max distance, then it will gradually switch between walk speed and run speed. If distance is lower than max distance value, we're going to set NPC can move to false. Otherwise, we'll set NPC can move to true, and we'll set the destination to target.value.position. And if distance is lower than mean distance.value, we're going to call a getaway from method with the target's position as parameter. So what the getaway from method will do, first we'll get the direction of movement using NPC position minus point. Then we're going to normalize this vector. Then we're going to compute a target position, which is going to be equal to direction multiplied by 5 plus the NPC's position. So we're going to go 5 meters away from the NPC's position. Then we're going to use navmesh.sample position with the target position. Remember to use unityengine.ai. So we're going to try to get this target position on the nav mesh. Then we're going to set NPC can move to true, and we're going to set the destination to target position. So this should allow our NPC to follow the target. Of course, we don't take visibility into account, and this is going to be an issue. So even if the target is invisible, the NPC will just stand there, which is great for now. So let's keep it simple and let's improve little by little. Let's go back to our Sentry behavior tree. In the parallel, let's add our new action here. So let's go back to our mind map. So we've done pretty much everything except shooting. But just for testing purposes, if the sentry shoots at me and the character dies, we will not be able to test all of these behaviors. So we'll ignore shooting for now. Let's just test these other ones. Let's get ready for our first combat AI. Okay, he's following me and aiming. So if I get too close, he will find a position behind and go back to it. Then he'll follow me again. If I get too far from him, he will start running to catch up. All right, this is good. Now let's add shooting. So let's do this cleanly. Let's add a task. Let's use a method called create shooting branch. So for the shooting branch, we'll create a sequence and we'll return a new repeater with that sequence as child. We want the NPC to fire in bursts, but first he's going to hesitate a little bit. So we're going to add a wait action here. He's going to wait between 0.5 and 1.5 seconds. Then let's add a timed repeater with a try shoot action. And the timed repeater will repeat between 2 and 4 seconds. So remember that 2 is the duration and 2 is the duration random. So indeed, it's going to be between 2 and 2 plus 2, which is 4. And we want this whole sequence to fail if we're not looking at the target or if the target is not visible. So let's set the conditions of the sequence to is looking at NPC and can see NPC. Let's create both of these actions. So in our conditions folder, let's create an is looking at NPC class, which is going to inherit from NPC condition. And we define the target and a couple of constructors. Then we override the onUpdate method. So this will return success if NPC is looking at target.value.sensor position. Of course, we check if target is null or target.value is null, and we return failure. In fact, here, if target is null, we should start printing errors on the console. We should be doing this in all the tasks that use a shared NPC. Then let's create a can see NPC condition inside the sensors folder. So this will return a success when sensor.isVisible target.value is true. In fact, you know what? Let's just check if target.value is null, and that should trigger an error message when target is null or when sensor is null. So if this is the case, we're going to get a null reference exception on the console, and that should tell us that something is wrong. So let's go to our Sentry. So here I'm just going to use the constructor with our target. This is a simpler syntax. No need to define the property between brackets. Yeah, that should do it. So the sequence will constantly check for these conditions. However, in our composite task, we forgot to add methods to change the evaluation mode of these conditions. So let's fix it here. Let's add 2 methods over here. So the first method is setConditions evaluation mode. Is going to set the evaluation mode on the condition. And the second one, setInterruptConditions evaluation mode, which will set the evaluation mode on our interrupt condition. So just in case we need to use them, back to our Sentry behavior tree. So in general, the end evaluation mode is fine for most cases. Okay, so our NPC will hesitate for a little bit, then we'll shoot a burst, then repeat. Okay, let's test this. It seems that our shooting sequence is not working. Let's disable the conditions. So the NPC is shooting at me. And since we've disabled the conditions, he's going to shoot whether I'm visible or not. Yeah, I'm dead. So he's going back to his post. Let's just use the can see NPC condition here. Yeah, so the repeater seems to be stuck. This reminds me of an issue that we've been getting when all the tasks in a parallel or parallel selector was stopped and the parallel was stuck, pretty much like the repeater here. So I'm guessing that the new conditions and especially the modifications that we made in the task class are interfering with the behavior of the repeater, or maybe all the decorators in general. You know what? Let's go back to our sequence and let's not do this in here. So in the onEntry method, let's just do it as we did before. Let's just start the child. Let's do the same in the parallel task. So we're going to remove this. We're just going to call onEntry and onExit one extra time, which is not that bad. So we shouldn't have bad consequences with that. So let's go back to our behavior tree and let's restore both of these conditions here. Now, hopefully it should work. Yeah, so now it's working. So the sequence is failing, even if it's colored in green. So after a while, the NPC will forget about the detection entry for the player and will go back to its post. If I emerge again, he's going to shoot me if I'm visible. Yeah, I'm dead. So he's going back to his post. I'm going to press 2 to revive. Okay. Let's try to escape. Yeah. So it's working fine. I'm going to set my health points to a big value just so we can see the burst shooting. So he's going to shoot for 2 to 4 seconds. Then he's going to wait and then shoot again. So we should probably add another wait because this first wait is for hesitation. Let's go back to our create shooting branch and let's add another wait here. So it's going to go from 2 to 3 seconds. Okay, so he's going to shoot me, then wait, then shoot again, then wait. If I'm not visible, he's not going to shoot. So if he's not looking at me, he cannot shoot. So if I'm behind him, he's going to turn. Now let's upgrade the behavior a little bit. Let's go to the follow NPC action. Here let's use a boolean, use last known position, and another boolean, require visibility. Right now the follow NPC action is kind of omniscient. So let's go to our maintain distance method. We're going to define a target position and we're going to use it in the code below. So it's going to be set to target.value.position by default. So this is the omniscient mode of the action. If we're using the last known position, we're going to get the detection entry of the NPC. Then we're going to set the target position to the last known position in that entry. In fact, let's go ahead and declare the detection entry here. So now for the distance, we're going to use vector tree distance between NPC position and the target position. And in the set destination, we're going to use target position here. And we're also going to use target position in the get away from. And here at the bottom, if require visibility is set to true and the entry is invisible, we're going to do the same thing that we're doing here. We're going to set can move to true, then set the destination here. Back to our Sentry behavior tree. Here when we're adding the follow NPC action, we're going to set require visibility to true and use last known position to true. Now the NPC will try to get to my position if I'm hidden. which is a little bit more effective than the previous behavior. So if I hide from him, he's going to follow me. So he's not going to be omniscient of my position. So he's just going to go to my last known position, as you can see here. So after a while, after the entry has expired, he's going back to his guardian post. So let's do this. Let's run away in front of them. So let's hide. Let's quickly hide. So he's going to get there and he's still going to look at me. However, he's not going to know my current position. He's limited to the knowledge of my last known position. After a while, he's going to give up. So this is a decent combat behavior that does a lot of complex things. So we're going to stop at this point today. And we're going to improve this behavior in another episode. And we're going to introduce other types of NPCs. So thank you for watching. Remember to subscribe and hit like if you like the video. Join our community of game dev beasts. Share this video with a friend. So I'm going to see you in the next video. Until then, take care.